First of all, I want to thank the organizers for possibility to give a talk. Yes, just a minute, please. I have problem. My screen is visible?
No.
Not yet.
Not yet. Okay, I will try again. Visible?
We have to wait. Oh, yes.
Yes, okay. Okay. As in a previous talk, let n r be the sets of natural and real numbers respectively, C be the complex plane, and C bar be its one-point compactification, U be the open unit disk, and R plus equals interval from 0 to infinity. Let B from C bar be a simply connected domain and point A from B. According to the Riemann theorem on mapping, there exists a unique conformal mapping of the domain B onto the unit circle, at which f of A equals 0 and f prime of A from R plus. If we consider inverse mapping C, which maps a unit circle onto the domain B, such that C of 0 equals A, then R big of BA equals 1 over modulus F prime of A equals modulus C prime of 0 is called conformal radius of the simply connected domain B relative to a point A from B. In 1934, Lavrentiev solved the problem of product of conformal radii of two non-overlapping simply connected domains. Lavrentiev proved inequality one for 2 points A1 and A2 for two fixed points of the complex plane C, and two domains B1 and B2 be any non-overlapping simply connected domains in C. Then the inequality one holds. Equality in this inequality occurs only in the case when the domains B1 and B2 are two half planes and the imaginary axis is their common boundary, and points A1 and A2 are symmetrical about their common boundary. This situation we can see on picture 1b. Later in the monograph by Schiffer and Spencer, a whole chapter is devoted to the study of Lavrentiev's prop theorem. Then many others investigated this result in a different direction. Then Lavrentiev's result was generalized to the case of meromorphic functions. In this case, for domains B1 and B2, inequality 1 is valid, and equality in this inequality is attended if domains B1 and B2 have the following form. An example of such configurations of the domains is the case when one domain is bounded by some circle, in this case B1, and on this picture B2, and other is unrestricted, that is a complement to the first domain. In this case, we have a whole continuum of extremals. Let G be a domain in C bar Z. By a quadratic differential in G, we mean the expression Q of Z dz square, where Q of Z is a meromorphic function in G. A circular domain for quadratic differential qz dz squared is called a simply connected domain G, containing a unique double pole of this quadratic differential in a point omega, such that at univalent conformal mapping, the domain onto the unit circle, the identity second holds. So thus in 1952, Kolbina summarized Lavrentiev's result by taking functions in a fixed positive degree. For any finite different point, A1, A2, maximum of the value, modulus F1 of 0 prime to the alpha, modulus F2 over 0 of 0 prime to the beta. She and Kolbina proved inequality 5. Equality in this inequality attended for domains that are circular domains of the quadratic differentials 4. On the picture E and F, we have this situation. Goluzin, in his monograph in 1969, generalized the Lavrentiev theorem to the case of an arbitrary finite number of mutually non-overlapping domains and obtained an accurate evaluation for the case of 3 domains. He proved inequality 6. If A1, A2, and A3 are 3 equidistant points on the unit circle, then equality occurs only in the case where the domains D1, D2, and D3 are bounded by rays emanating from the origin at equal angles to each other and containing points on their bisectors. On the picture, we have extremal configuration when we have equals. Further, Kuzmina showed that the problem of the evaluation for the case of 4 domains is reduced to the smallest capacity problems in the Saturn continuum family and obtained the exact inequality for 4 domains and proved inequality 7. Equality occurs only in the case where the points -1, 1, and A equals plus minus I square root of 3, form a regular triangle. The extremal configuration corresponds to a continuum, -1, 1, E square root of 3 unit in 3 segments of equal length. On the picture, we have this extremal configuration when we have 4 domains, D1, D2, D3, and D4 containing infinity. Problem of finding estimate product K from 1 to 5 modulus Fk of 0 prime was solved in the works of Dubinin and Kuzmina under the additional assumption that the quantupole A1, A2, A3, A4, and A5 is symmetric with respect to a line or a circle. And they obtained inequality 8. Equality in this inequality occurs for points 1 e to the minus 2 pi I over 3, 0, e to the power 2 pi over 3, infinity, and domains dk, k from 1 to 5, which are circular domains of the quadratic differential 9. On the picture, we have this extremal configuration, when in this inequality, we have a equals. Now, as ultimate results in problems of finding estimate of this product for n is greater than or equals 5 are known at present. Well, Lebedev considers the more general problem. He considers product 10. A lot of others engage in these topics. In 1988, Dubinin proposed a very efficient approach, method of separating transformation based on the method of symmetrization. And using the methods, he obtained a solution for a number of extremal problems for all n. N is greater than or equals 2. The method essence is in the next. The object is divided into the parts, which are mapped on a part of a special form. Then from the last part, symmetric items are constructed by gluing or by one of the known methods of symmetrization. The importance of the separating transformation is that in some cases it allows the problem with a lot of parameters to reduce to a number of similar problems with fewer parameters. A function gb of za, which is continuous in C bar, harmonic in B minus A apart from Z, vanishes outside B, and in the neighborhood of A has the following asymptotic expansion: G sub B of za equals minus logarithm modulo Z minus A plus delta plus infinitesimal value z tends to A, is called the classical green functions of the domain B with pole at point A. The inner radius small r of BA of the domain B with respect to a point A is a quantity e to the power delta. Analogically, if the inner radius r of B infinity of the domain B with respect to infinity is the quantity e to the delta. In this case, green function g of bz infinity equals logarithm modulo z plus delta plus infinitesimal value that tends to the infinity. The inner radius is a generalization of conformal radius for multiply connected domains. If we have simply connected domain, then inner radius coincides with conformal radius. In previous works, we considered a system of points of the unit circle or circle of the radius r. This situation we have on the picture A. We considered n-radial systems of points when we have n rays and each ray has one point, picture B, and we considered an m radial system of points when we have n rays and each ray has m points, picture C. In this work, we consider any fixed system of points of the complex plane. For example, it is P rays, and each ray has a different number of points. And sum of these points equals n. So in this work, for some value gamma, we consider the following functionals. In of gamma equals inner radius of the domain B0 with respect to the to 0 to the power gamma. Product k from 1 to n r of b k a k. Functional y n of gamma equals this value, and functional jn of gamma equals r of. Unfortunately, I have a problem. My screen is black, so I will try to connect with phone. Can everybody to close this presentation, and I will try again.
Okay, you can try again.
Okay, thank you. I will try. Okay. So in this work, we consider any fixed system of points of the complex plane, and we consider these three functionals: in of gamma, yn of gamma, and jn of gamma, where n belongs to the set of natural numbers, an is any fixed system of points of the complex plane, domains B0, B infinity, Bk is any system of mutually non-overlapping domains such that functionals of type 12 are called functionals of the first type. To the second type, we will carry functionals of the kind 13. To the third type, we will carry functionals of a kind 14. And for functional in of gamma, we proved dynamic inequality 15. In this inequality, functional is determined by their initial value of this functional. So we prove theorem 1. Let n from n, gamma from R plus, L plus equals interval from 0 to infinity. Then for any fixed system of different points of the complex plane and any mutually non-overlapping domains, we have inequality 15. The partial case of theorem 1 for NM radial systems of point at A is greater than or equals 2 was proved in paper 13. Also from theorem 1, if gamma equals 1, we obtain the following statement. Corollary 1. For any fixed system of different point of the complex plane and any mutually non-overlapping domain, the inequality R of B00 to the n product k from 1 to n r of bk ak is less than or equals n to the minus n over 2 product k from 1 to n modulus ak squared is satisfied. Inequality 16 we will call the generalized Lagrangian inequality, because if n equals 1, then from corollary 1 we have the Lagrangian result. Inequality 16 and the additional conditions on the geometry of the location ak, k from 1 to n clarifies the Lagrangian result. And we have corollary 2. Let n from n, then for any fixed system of different points such that modulus ak equals rho from r plus for all k from 1 to n and any mutually non-overlapping domains, and the inner radii are equal, then inequality r of b0 0 r of bk ak is less than or equals 1 over square root of n rho squared for all k from 1 to n is valid. On the other hand, under the condition of this corollary 2, from theorem from the Lagrangian theorem, we have the following inequality: r of b0 0 r of bk ak is less than or equals rho squared for all k from 1 to n. And for functional yn of gamma, we obtained similar dynamic inequality 18 for all for any fixed system of different point and any mutually non-overlapping domains. The following inequality holds: yn of gamma is less than or equals n to the minus gamma of 2, yn of 0 to the 1 minus gamma over n. The partial case of theorem 2 for n m radial system of points at A is greater than or equals 2 was proved in paper 15. From theorem 2 we obtained the following statement. If gamma equals n, then we have inequality 19 for any fixed system of different point and any mutually non-overlapping domains. The inequality r of b infinity to n product k from 1 to n r of bk ak is less than or equals n to the minus n over 2. For the case of an infinitely distant point, inequality 19 also is called the generalized Lagrangian inequality. Corollary form: let n belong from a set of natural number, then for any fixed system of different points and any mutually non-overlapping domains, and the inner radii are equal, the following inequality holds: r of b infinity r of bk ak is less than or equal 1 over square root of n for any k from 1 to n. At the same time, the following inequality follows from Lagrangian's corresponding theorem: r of b infinity r of bk ak is less than or equals 1 k for all k from 1 to n. And finally, we consider functional Jn of gamma equals this value. Theorem 3. Let n from n, gamma from r plus equals interval from 0 to infinity. Then for any fixed system of different points and any mutually non-overlapping domains,
B0, B infinity, Bk, k from 1 to n. The following inequality holds. Jn of gamma is less than or equals n plus 1 to the minus gamma n plus 1 over n plus 2, Jn of 0 to the 1 minus 2 gamma over n plus 2 on product k from 1 to n modulus ak to the 2 gamma over n plus 2 if gamma from interval 0 n plus 2 over 2 and the functional Jn of gamma is less than or equals n plus 1 to the minus n plus 1 over 2 product k from 1 to n modulus ak if gamma is greater than n plus 1 n plus 2 over 2. The partial case of theorem 3 for nm radial systems of points at n is greater than or equals 2 was considered in paper 16. From theorem 3, we have the following statement. If n from n and gamma is greater than n plus 2 over 2, then for any fixed system of different points such that modulus ak equals r from r plus for all k from 1 to n and any mutually non-overlapping domains b0, b infinity, bk, the inequality 21 holds. And we have corollary 6 from theorem 3. Let n from n, then for any fixed system of different points, such that modulus ak equals r, and any mutually non-overlapping domains b0, b infinity, bk, and in this case the inner radii are equal, the following inequality holds. R of b0 0, R of b infinity infinity, R of bk ak is less than or equals n plus 1 to the minus n plus 1 over 2n modulus ak for all for any k from 1 to n. Thank you very much for your attention.